8 chips, and it's all mine. Now, obviously, I didn't run away with the box, but what I'm standing in front of is Tenstorrent's second generation of dev kit. You may remember the first generation. We sat here in the office with one of their senior developers, Jasmina, to speak about the PCIe card. Well, now they've done one better. What we saw then was Grayskull, the 75-watt version and the 150-watt version. What we have now, and make sure I get this the right way around, is Wormhole. Black holes later, this is Wormhole. What we have is their development system, so this is the dev kit, and the full quiet box. If you really want the powerful hardware, it's in here. They're also doing PCIe cards. You can get a 150-watt Wormhole chip or a 300-watt with 2 Wormhole chips. The whole point of these dev kits is to bring people into the Tenstorrent world of AI. All the software is open source. They have a community. You buy the card or the system, you go online, and you can just simply install and start developing for your AI workloads today. If you're an end user just interested in playing with an AI ASIC, or if you're a business with an AI workload in mind, the whole point of these things is that they're accessible and easy to use. In this video, we're going to go through what these systems entail, and luckily this dev kit is pretty bang on for the hardware, but we'll also see the other one. We'll also speak to Jasmina again about what Tenstorrent are doing with their software stack, because since we spoke to her last, there have been some major developments. We'll also see some workloads running on this system as well, just to prove to you it is working. And trust me, it is. I've seen some impressive numbers while I'm here. We won't be able to show all of those today, but maybe in a future video we will. And then, because Jasmina is part of a power couple with Davor here at Tenstorrent, we're going to speak to Davor about the hardware, about some of the new interesting formats we're seeing with the hardware and advances in AI. This is really exciting. You don't want to miss out. What's your minimum specification? So as I said, this is the dev kit. This is what they built before they got proper designers in to do the actual kit, but the hardware is practically identical. All liquid-cooled system. There's this blue coolant that lights up purple because they've adopted a new purple color scheme. But the chip inside, the CPU is an AMD Genoa Zen 4 chip with 512 gigabytes of memory, 8 channels, as you might expect. But the important stuff here are the AI cards. We have 4 of the 300-watt Wormhole cards featuring 8 chips altogether. They connect here with something that kind of looks like an SLI bridge. And you may remember we had multi-GPU a while back, but for AI, having that chip-to-chip connectivity is ever more important. What it is here is basically standard Ethernet. We've got 400 gigabit Ethernet per chip. So ultimately, you can connect to all the cards in the system, and then you have 2 connections out the back to other systems. The point here is with this box, you play around, you have the 8 chips on board. You then scale up to one of their Galaxy data center massive rack units. It's about 4 or 5U. But the whole point is one system looks like one rack, looks like one supercomputer. The way you program these things is very how programming should be, right? You want it to be simple, and that's the whole point when I first spoke to Jim Keller at this company is let's make the compute for this, as intuitive and as simple as possible. So I'll show some B-roll shots of the quiet box, this big purple one over here. We decided not to open it up because they're actually going to show me demos of it in a second. But with this, dev kit, the hardware is practically identical. If you want to get the quiet box, it's a 15 grand expense, but you get 4 of the cards and the support and the community and everything else. They do have an air-cooled loudbox version for 12,000, or you can buy the cards individually. It's 1,000 for the 1-chip card or 1,400 for the 2-chip card, all available on Tenstorrent's website. we're actually now going to have a look at the quiet box running some workloads. And I'm going to get Jasmina in to talk about what we're seeing. So followers of the channel will recognize Jasmina from Tenstorrent, senior software architect, developer, background in FPGAs that a lot of you seem to like last time. But what we're in front of is one of the quiet boxes running Llama right now. We'll get to what it's showing in a second, but I wanted to get Jasmina on to talk about what's changed in the software in the last 8 months, because it's been a while since we spoke. How are you?
Great. I can't believe it's been a few months. Yeah, it's been a super wild ride. So we open sourced last time we met, we open sourced and we were super excited about that transition. Since then, we've been embracing the open source community. We love the open source effort and sort of engaging with folks online. People who are ordering our dev kits, the ones that we open source together. And now we're getting super excited about delivering the boxes.
I mean, literally as we're recording this, I saw people even writing their own research papers with the dev kits coming out. So Moritz, if you're watching, we definitely saw it.
We loved it. We loved the paper. That was really exciting. I love the way that he explains the programming model. And then for us to see sort of that reflection of our internal understanding reflected externally, it was an amazing feeling.
I think that was some of the feedback I gave to your team last time I was here. I mean, you gave me a deep dive into how the architecture works from the software perspective. But that wasn't ever mentioned externally in a formal way. It was in the code base.
Yeah.
And then this guy did it in a research
paper. And this guy did it, yeah. And it's like we have documentation that's out there, and we are writing papers of our own, and we're sort of contributing to the body of knowledge that's in print. But that's, it's somewhat lagging the fast pace of development that we have, right? And we're never going to be able to document everything that we develop, and most of our documentation is in the code. Right, so there's a decent amount of effort on making the code readable and understandable, and such a research paper that we see out there is a proof of that. So that's super exciting.
So I want to talk about how many dev kits you've sold, but obviously you won't give me that number. That's proprietary. But it sounds like the response has been good, so hence the second generation.
That's right.
So what does the second generation bring that the first one that we saw in the last video didn't?
Oh, that's a good question. So the second generation is native scale-out. Wormhole devices have Ethernet cores on them, and one way that we think about it is it's a donut of communication around a middle of compute. And so you can Tetris these devices together, and you can create a mesh of scale-out, which is super exciting. You could interconnect it with cables or T-flies, the little PCBs on top of the cards.
Yep.
And the boxes that we're selling and the cards that we're selling, they're the dev kit version of sort of the scale-out enterprise server systems that are coming soon.
So why is scale out important? What are you seeing in the customer base that says they need scale out?
I mean, inference training, large workloads.
Everything AI.
Everything AI, that's right. Everything AI and HPC. And what we want to do is to deliver a dev kit into the hands of folks at home that can then play around and write kernels and sort of just get a really good deep dive understanding of what the hardware is without having, before they order the really big systems, which are an investment.
So talk to me a little bit about how you're managing the community, the people who have managed to get the hardware, or they're just playing around with the open source code and whatever.
Oh, cool. Yeah. So we have a Discord channel that we really enjoy interacting with folks on there. We're super excited to highlight contributions from the community. We are ourselves, I heard somebody say, best way to sort of have open source community engage in your open source project is to contribute to other open source projects. And I really like that. So we are integrating our software into VLLM. We have a native integration into PyTorch 2.0. We also have we spun up a new internal effort called Forge, which is an MLIR-based compiler, which has multiple integration points and sort of like a funnel from multiple front ends. So the really fun part is that we are integrating into the ecosystem, and that's been a wild ride.
So on this TV, which I've turned down the brightness, and you'll probably see me blur a few things that we can't show. We're actually tapped into the quiet box over here, the one with 8 chips, 4 PCIe cards, running language models. Talk us through what we're seeing.
That's right. So this is a Llama 3.1 70. It's running Tensor parallel. tensor sharded on the box of 8 devices. So this box is a grid of 2 by 4.
Yep.
And so you can configure the 8 devices in various ways. You can either have a model that targets each of the devices independently in a data parallel way, or you can shard across them if you have large ops and large tensors. So this one is running in a tensor sharded way. It's sort of a miniature representative of the larger scale-out systems, of the galaxies and some of the enterprise systems that are coming down the line. And the programming model is the same. So the kernels that we're writing here and the way that we scale out from 1 to 8 chips is exactly the same way that we're going to scale out from 8 to 32 and then beyond.
So you can literally take what you've done on the dev kit, plant it in the data center.
That's right.
No adjustments or pretty much no adjustments?
Well, these cards run the same way in the data center. We adjust. You can adjust the topology of the devices themselves. So there's that setup to sort of once the host sees that cards are in the system, you can configure them in various ways. And because there's cabling that we ship with the cards, and you can cable it various ways.
You literally do physical.
You can literally
topology or
that's right.
software topology.
And then you define in the software.
Yeah.
So what you do physically with the cables, you define with the software.
I mean, it's we were talking a little bit about this earlier. You've got 8 chips, but 32 concurrent models running here.
So this one is one model. This is a large Llama 7.
But sorry, I mean 32 users.
32 users, that's right.
Right.
So this is a batch 32.
Okay, yeah.
And then it's prefill followed by decode.
Yeah.
So it's just a classic LLM end-to-end demo.
So it means it's going to have the relevant benchmark numbers that a lot of people are trying to talk about. But
yeah, that's right. So we keep those updated on our website, on the GitHub repo. So we have a table there with the models that we brought up and some of the performance. We have performance updates almost weekly. So best of the latest and greatest is there, including some of the targets.
Very much alive.
Very much alive, living, breathing.
This is where she tells me they're hiring right now.
That's right.
Yeah.
We are hiring.
So what do you want to see as part of the community and the models and the bring up going forward as these dev kits are put into the hands of people?
Oh, that's a good question. So we're super excited about the pace of LLM research and innovation there. It's really interesting to see how many research papers there are on different techniques. We want to expose the kernel development model and sort of reinforce that with the dev kits and have that bottom-up sort of adoption and people feeling really comfortable with like ordering a box and then opening up the code, writing a kernel, running it on the hardware, posting a bug, right? Another interesting thing is that we're setting up CI on our cloud so that we can actually enable some external developers to come and run our CI and then be able to commit the code. So that's kind of like the next step in our maturity as an open source platform.
How many cards do you have at home?
Too many.
Too many. Too many.
That's right. Well, one of the reasons is why we made a quiet box is because it was too loud, right, to have at home. And so we want to have it at home. Yeah. And we want it to be quiet and friendly.
So that's Jasmina. I'm going to pivot over to Davor now. He's standing very patiently by a whiteboard. And it's really amusing that Jasmina and Davor are a couple as well, being at Tenstorrent. So let's pivot over to Davor and talk more about the hardware. So as promised, I'm here with Davor, senior fellow here at Tenstorrent, who's going to take us through hardware and some of the new features on Wormhole. And it's you were showing me this mesh a little while ago.
Yeah, so this is what we have within the quad box. It's 2x4 mesh of wormholes. It's 4 PCI Express cards. Each PCI Express card has 2 wormholes. Wormholes are interconnected into a 2x4 mesh. And as Jasmina described earlier, this is a smaller instance of our servers. Our servers are bigger meshes and clusters are interconnected meshes. So with this small dev kit technology, you can learn all about the key features of Tenstorrent.
So does 2x4 bring in some interesting, topology? Or is just 2x4 the easiest from a physical perspective?
2x4 is actually interesting because you can play with a couple of interesting data movement patterns here. So you could take these 8 chips and think of them as a ring. So you can move the data very efficiently in a ring, or you can think of it actually as a 2x4 and then have data be multicast across rows or columns. Yep. So then you're exploiting the actual locality in the column direction or row direction. Okay. So it's a good instance to experiment with various data movement. So what else do we got? So we have 100 gigabits per second, 4 links. So in total, that's 400 gigabits going into each wormhole, which is 50 gigabytes per second, which is in the dev kit pretty solid bandwidth. In our bigger systems, the bandwidth is 4 times more than that. And so what else we are not showing here? It's DRAM. So each of these has DRAM connected to it, and each of these is 288 gigabytes per second of DRAM. So on aggregate, when you have distributed DRAM,
about 2 terabytes per second.
it's about 2.3 terabytes per second. So you can think of this system as a distributed DRAM, and then we shard the weights in the demo that Jasmina was showing. The Llama is in the Llama demo, the weights are sharded, but the aggregate DRAM bandwidth that we can get is 2.3 terabytes.
That sounds a multiple of what NVIDIA can provide on one chip.
Exactly, and what's amazing about this approach is that each of these wormholes needs to saturate its own DRAM. So often, if you optimize a wormhole to saturate its own DRAM, then on aggregate you get 8 times that. And this scales to bigger meshes. Right? You essentially get the mesh of DRAM. So you can think of that this is you can think of this as almost as a DRAM server in terms of LLMs, and then you have networking in DRAM and compute in DRAM.
So each one of these chips, it's 12 gigabytes of GDDR6, right?
Yes.
Why 12? Because I know a few people will say that's not enough.
So in total, that gives us on aggregate 96 gigabytes per second. So that brings us to our data format.
So 97 gigabytes of
capacity.
That's 2.3 terabytes per second.
Yeah, that's the bandwidth. This is the capacity. Yes.
Yeah.
Capacity is 96 gigabytes of capacity, which in 8-bit it can comfortably fit Llama 370 plus some decently sized KV cache. But it goes beyond that. So we have a range of low precision floating point, which is.
So I wanted to bring it over here because you've probably seen the video I've done on micro scaling with NVIDIA's hardware, and in that I spoke about block float support, and I said it's really hard to enable block float support natively, and this is kind of what Tenstorrent's done. And I actually like the way you've presented it here because trying to tell people about block float is kind of difficult.
Yeah, it's. So in the demo, we're using the block floating point 8.
Yeah.
So the reason why we're calling 8-bit is because of mantissa plus sign, but there's more to it. So let's start from the left. So we have an 8-bit exponent, and then we have a block or a group of 16 numbers. They share this exponent, and then each of these numbers in the block is sign plus mantissa for 8-bit. This is where the 8-bit comes from, but it's a group of 16 and a shared exponent of 8-bit. So what's great about it is that the 8-bit exponent keeps all the dynamic range, and seamlessly you can convert from a FP32 like single precision or half precision to this.
The way I normally explain this is you've got the accuracy, you've got 8-bit accuracy here, but then you've got an additional 8 bits of range, and because you apply it to all 16 numbers, they all share the same range. This penalty is a minor overhead compared to the math of this. And I think that's the way a lot of LLMs or general AI is going in order to extract performance.
Yeah, we find that across LLMs, most of them seamlessly without loss of accuracy go to 8-bit version of the block floating point. But then we on top of it have the 4-bit and 2-bit version, which we're super excited about.
Yeah, so this is pretty much research still, but people acknowledge it. This is leading edge. People really haven't tried it properly yet. So
we were really excited then to enable developers to be able to start experimenting with this now, because we already have this in our current generation dev kits, and the future architecture will take this to the next level. But you can already take it and try like 4-bit and 2-bit. So 4 bits, same idea, just mantissa is 3 bits, sign is 1, so that together they make 4. It's still a block of 16. 8-bit exponent remains, so the range is there. So again, you can just seamlessly keep reformatting into smaller and smaller precision, and then
FP2. So you got 1 sign bit, 1 mantissa, So that's either a 0 or 1. This is, I mean, I can imagine us doing unsigned FP2 to actually get 2 bits in there.
Yeah.
But this is almost binary compute.
Yeah. So this would basically correspond to the ternary ternary weights paper. It could be code -101 with the addition flexibility that you still have the range of the exponent. So you could shift the numbers in each group of 16.
I mean, I think we're seeing with traditional FP8 right now, the 3 bits for mantissa, 5 for exponent, or 4 and 4 for training versus inference. This is kind of flipping it on its head by saying you can still have all that range.
Yes.
But
yes.
if we can manage the accuracy, this mantissa down, then it's all gravy.
Yeah. So our goal, what we're working on is that we would be natively training neural networks in this format, right? So you can start with FP32 and then you switch during training to bfloat 16, and then progressively you lower the precision. So you would want to end up your weights frozen finally at the lowest possible precision.
Yeah.
And during training you can seamlessly reduce the precision as the training converges, so that at inference time you have a much more efficient solution. And so going back to the capacity you're asking about 96 gigabytes. So
at BFP2,
this can almost fit a 4 or 5 Llama 3, right?
Yeah.
A 400 billion parameter. If it was, let's say, either fine-tuned or post-trained in this precision, right?
Yeah. And that's all in memory as well.
Yes.
Right.
Yes.
I think that's important. You could do a 400 billion parameter model.
Yes. Yes.
But the time to first token would be terrible and whatever. But being it natively in memory, you get all the performance back.
Yeah. So in fact, like if you took a 400 billion model and you converted it to 2-bit block floating point, and you ran it at 2.3 terabytes of memory bandwidth, you would actually get like around 5 tokens per second per user for a batch 1, which is pretty amazing on such a small system, right? So
have you done that internally yet?
We're working on it. So
we're working on it. Watch this space. It'll be in their GitHub soon enough.
Yeah, as Jasmina said, all the updates, all the progress is just live on our GitHub. Updates on the models, systems, and the servers with the bigger versions of these meshes and with more bandwidth with 4 times more bandwidth, and 32 chips and even faster DRAM is coming later this year. So we're super excited about it.
Is there anything else that's different with the server architecture?
It is the exact same architecture. It's a bigger mesh. It's 4 by 8.
Okay.
Versus 2 by 4. It will be able to be a 2D torus.
Yeah.
If you wish it to, you can take the edges.
Yeah.
You can make the edges wrap around and make it into torus, or connect multiple servers into a bigger mesh. So you could create a mesh of 8 by 16, right, or bigger, and then that's the scale up into a bigger mesh, and then we interconnect the meshes into a generic topology. So
that's a quick look at the Quiet Box. This is essentially the near finalist design. There's a few little kinks to work out. There's some condensation in the reservoir, but this is ultimately what a Quiet Box is going to look like when it arrives on your doorstep. Very much attention has gone into the design and the idea of this thing. Functionally, it's, as we've spoken about with Jasmina and Davor. Inside you have 4 of these Wormhole cards, 2 chips with your connectivity ports on the back, and then also your connectivity ports inside to enable it. It looks like a hell of a system, and we're seeing some of the tests running on it already. As this video goes live, these should start shipping soon. This is literally the first complete one they've got in the office before they send off, for the production run. And I will say, apparently these purple LEDs are RGB, so if you really want to do a green one or you want to do a custom decal, you can do that as well. There has been sizable interest for these. I guess more than Tenstorrent was expecting. I mean, it's not earth-shattering by any means, because it is an expensive system. Was speaking with Jim Keller between yesterday when I filmed most of this video and today when I came back, And he turned around and said, they initially built what they called the loud box, the one that is air cooled, the one that's got to deal with pushing all the air through this thing. And he said after a few minutes, he asked them to go out and build a quiet one. Because if you put multiple of the loud boxes, it gets kind of loud. But if you only need one, then a loud box is easily doable. I'm, 3 inches, 2 inches away from this system. I can barely hear it. It's clearly been designed with that in mind, with how the airflow comes in the bottom. Now, you see, the funny thing is, I spent time here speaking with Jim, and he said there's an interest from a section of the community who want to use one of these Wormhole chips, not as an AI accelerator, but as a network switch, because it just has so much onboard networking, and the cost situation for the chip makes sense. That you could imagine in a system, if you want to do a massive interconnect between all the systems in the office, you have your CPU, you have your GPU, you have your AI accelerator, and you have your high-speed networking. I mean, hundreds of gigabits per second per port, per card. And even if you don't need to use the AI compute, or maybe you use it for security or whatever, it just ends up being networking rather than just simply compute. Ultimately, we might see Tenstorrent end up in the networking business. I say that semi-jokingly because that's not necessarily a goal of what Tenstorrent's trying to do here. But it is amazing that you can build something so network-focused on the AI side and end up being an option for a completely different market you weren't expecting to be. I talk a lot with my clients, with investors, about what AI companies are going to succeed, right? And let's be serious. Most of the times when we speak about AI companies, and especially startups, there are 4 companies that we speak about. Tenstorrent, Grok, Cerebras, Samba Nova. They're the ones that have all raised the big money. They're the ones that are all mostly to succeed. And pretty much every one of those has a piece of hardware that does more than simply just AI. I wish we knew a bit more about Samba Nova. The SN40L is their new chip. We know about Cerebras. We know we wish we knew more about Grok, and ultimately, all their competition is Tenstorrent, and then all of them are competing against NVIDIA. Not going to beat around the bush here. It's a market that's going to consolidate at some point, but it's the companies that offer more than just simply AI. AI with switching, AI with CPU compute. The fact that Tenstorrent's going down the RISC-V route with their Ascalon core, 128 cores of high-performance RISC-V. I've got a video on that you can see on this channel. It's actually doing really well, and a lot of people learn a lot about RISC-V due to it. I should probably do an update kind of soon. I spent time here speaking with Weihan, their lead architect for their RISC-V core. Again, you can go see that interview. That was his first time on camera, and he did really well. Had a chance to speak to him and had dinner with him last night. And we got to speak more about what the industry needs and how the industry is going to perceive high-performance RISC-V in the market. Maybe we'll do a catch-up interview with him soon as well. If you want that, put a comment down below, and we'll see if we can make that happen. Tenstorrent seems very ready to throw engineers at me. I just need to make sure Jim's available for another interview. I wish I could open it up. There is a number of standard screws, but I'm not sure I'll actually take the right ones out to open the side panel off, because it's not a standard chassis. You can do it. I just ran around with the dev kit just in case, because if I was going to break this one, it was going to be coming out of, I'm going to get a big bill to do it. But this is essentially being Tenstorrent's quiet box paired with their, Wormhole 300 S card with 2 chips on side, leading their way onto the future of Tenstorrent with Black Hole. Black Hole's coming very soon, and it's going to showcase more of what the next generation Tensix, what you get when you add in RISC-V cores as compute as well. The software, forwards compatible, as with a lot of Tenstorrent things, gonna maintain that community, maintain that open ecosystem, maintain the open source, and we'll see how we go. If you want one of these, there'll be a link in the description for a competition. No, there's not going to be a competition. Don't worry about that. I wish I could. I wish I could. We'll see what they say, and maybe we will be able to give some of these away. But thank you for watching, and we'll see you on the next one.